Welcome to T2, day 29 of calculus. Let's go back to creating two circles of fencing. So we have two circles, circle 1 and circle 2, and it's telling us let's use radius of circle 1 is x and the radius of circle 2 is going to be y. So what do we now know? We know that circle 1 has to contain at least 20 square feet of fencing. So we know that pi x squared has to be greater than or equal to 20 pi. And the other one, the other circle, circle 2, must be at least 50 square feet. So we know pi y squared has to be greater than or equal to 50 pi. We also know that the circumference of circle 1, we're calling this circle 1 and this circle 2, the circumference of circle 1 is 2 pi x, and the circumference of circle 2 is 2 pi y. Pi times diameter, diameter is 2 times the radius. So what does this tell us? Well, it tells us that if you simplify this, you get x squared has to be greater than or equal to 20. So therefore x has to be greater than or equal to the square root of 20, which is about 4.472. So we have the minimum value for x. That's the minimum value for x. Let's do the same thing for y here. We therefore know that y squared has to be greater than or equal to 50. So therefore y has to be greater than or equal to the square root of 50. So that's the minimum value of y right there, but we'd really like to know what the maximum value of x is. Well, to do that, we need a relationship between x and y, and we know that the sum of the amount of fencing used has to be equal to 100. It tells us that's 100 feet of fencing. So we know that 2 pi x plus 2 pi y has to equal 100. So therefore pi x plus pi y is equal to 50. So if you keep on going with that, we can solve for y. So if we do that, we get pi y is equal to 50 minus pi x. Divide both sides by pi, and you get 50 over pi minus x. So dividing by there. So what does that tell us? It tells us that y is equal to 50 over pi minus x. So if this right here is the minimum, square root of 50 is the minimum y value, when y is minimized, x will be maximized. So again, this is the minimum value y can take. So when y is minimized, x will be maximized. So what we want to do is to find the x max. We want to plug this into this equation. So we have the square root of 50 is equal to 50 over pi minus x. So add x to the other side. So x is equal to 50 over pi minus the square root of 50. So that's the x max right there. So what does this tell us? Let's just consolidate this a little bit. So x has to be greater than or equal to the square root of 20. And it has to be less than or equal to 50 over pi minus the square root of 50. You're limited in that way. So these are really important numbers to know right here. And that's a 50, not a 30 right there. That's a 50. Okay, so let's keep going here. So what is it asking for? What is the minimum possible area? The minimum possible area. What is the minimum possible area? So to do that, we need to write an equation for area. We need to write an equation for area. So to do that, we know that the area, the first one is pi x squared, and we know the second one is pi y squared. Those are the areas of both of these right here. So the area total is going to be pi x squared plus pi y squared. To find a minimum, we need to take the derivative, but we don't like having two variables, so we need to get rid of one of them. Luckily, we know that y is equal to 50 over pi minus x. So you take this y value and plug it in right there, and you end up with area is equal to pi x squared plus pi times 50 over pi minus x squared. And we're going to do our tried and true method of taking a derivative and setting it equal to 0. So when you take the derivative and set it equal to 0, and you take the derivative and set it equal to 0, I'll let you do it out and show that x will equal 25 over pi, which is about 7.957. So that's our value that we want to check here, and we need to use a sign diagram, which is 7.957. This is the x values, and this is going to be a prime of x right there. So we know that the max x value was this 50 over pi minus the square root of 50. That's the max x could be, which is about 8.844. We know the minimum is the square root of 20, which is 4.472. So when you do this out, it turns out that when you do the sign diagram, you're going to have these two regions, the blue region and the green region right here. It does turn out to be negative, 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 negative for the derivative, and then positive, 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 positive. And the derivative, you have to figure it out in this work here. That's what you plug into. You know, therefore, the function is going down then up. So this is going to be a minimum will occur when x is 7.957. So now what you want to do is you want to figure out what the area is, like what is that minimum area? Because I think it says that what is the minimum possible area. So these are the x values, so we think the minimum is going to occur here. Let's just test it all out. What's the area when x is 4.472? What's the area when x is 7.957? And what's the area when x is 8.844? You need to plug that into the original area function, and that original area function is right here. But you want it in one variable, so you're really plugging it in right there. Those are the x value, area in terms of x. When you plug in those values, you end up with the following areas. You end up with those final areas, and that tells you, look, it tells you that the minimum does actually, sorry, I flipped those numbers there, but now it's correct. The minimum does actually occur right here. So the minimum area would be 397.887, and this is going to be feet squared, I think it's feet squared. And then, so this is the min, and then our max is occurring over here. So our max is when x is equal to the square root of 20, which is what we need to answer to, because it also asks us for the maximum possible area. So we just found the min and max. Okay, so let's now build a Coke can, or in this case, excuse me, a Pepsi can. So we're going to build a can that's a cylinder. So we have a cylinder, and the volume will be 355 milliliters. So that's going to be equal to one liter is one, you know, now I'm just wandering with units. We can just keep it as 355. So let's keep it in milliliters. We don't have to actually use this right here, but it's there for your knowledge. So it's a cylinder with aluminum sides, top and bottom. Aluminum is expensive, and PepsiCo wants to use the least amount of metal possible to save costs. Find the dimension of the ideal soda can. So what we're doing is we're finding the minimum volume. The minimum surface area. So we know that the volume is going to be the same, but we need to minimize surface area. So we want an equation. We want an equation for volume that involves the surface area, the amount of aluminum. So if you were to unfurl this can, the side would turn into a rectangle, and you'd have the top and the bottom. Okay, so let's say that we did it in terms of, let's do it in terms of r. The radius of the top and bottom is going to be the same for both. So how much aluminum is used right here? Well, pi r squared square what are we using here? Just as a side note, it is important to realize that a milliliter is equal to 1 centimeter cubed. It's important to note that. So the amount of aluminum in the top is going to be pi r squared. The amount of aluminum in the bottom is going to be pi r squared. Now the key to realize here is that the circumference of the top and bottom, will also be right here. So the circumference, when you unfurl this green has to wrap around the top and bottom. That will be the circumference. So the circumference of that circle is going to be 2 pi r. That's the distance from here to here. And this right here is the height of the can, which we don't know. So what's the area of aluminum right there? The amount of aluminum around the side of the can is going to be 2 pi r times h. And then on top, it's going to be 2 of those. You add them together, you get 2 pi r squared. So what is the total aluminum? I can almost spell total here. The total aluminum will be 2 pi r times h. That's the aluminum from the sides. And then the aluminum on the top is going to be 2 pi r squared, because the top is pi r squared, the bottom is pi r squared, so there's 2 of them. So that's the total amount of aluminum. So we have 2 variables. Can't quite do any calculus yet. But we know that the volume, which is pi r squared times h, the volume of a cylinder, that volume has to be 355 right there. So if we do that, what does it tell us? It tells us that h is equal to 355 over pi r squared. So what can we do with this? We can take the h and we can plug it in here. And if we do that, the amount of aluminum will therefore be 2 pi r times h, which is 355 over pi r squared, plus 2 pi r squared. We now have a single variable equation for the amount of aluminum. So now let's rearrange this a little bit. And if you arrange this a little tiny bit and cancel a few things, what happens here? Well, the r cancels in one place, and so does the pi. So that's gone. One of those r's cancel. So what do you end up with? You end up with 710 over r plus 2 pi r squared, which is pretty nice. So now let's take the derivative. And it's key to remember, I'll actually back up for a second. This is the same thing as 710 times r to the negative 1. It's key to remember that. So now let's take the derivative, a prime. So it's going to be negative 710 r to the negative 2 plus, drop the 2 to the front, 4 times pi times r. And we're going to set that equal to 0. So 0 is equal to negative 710 r negative 2 plus 4 pi r. So 710 r to the negative 2 is equal to 4 pi r. And to the negative 2 power means this r, just the r, that negative 2 power is not touching the 710. So it's 710 over r squared. It's going to be equal to 4 pi r. That'll put it over 1, just like that. So now let's cross multiply. 4 pi r cubed is equal to 710. So r cubed is 710 over 4 pi. So r is equal to the cube root of 710 over 4 pi. And if you use your calculator, which you really have to do to get that, you end up with r is going to be equal to 3.837, and that's the radius of the ideal can. You also need to do a sign diagram to prove that you're minimizing the area function, so you would use a prime here, and it is a minimum. But if we want the h value, so that's the r value, remember what's the height of the can? We had a relationship up here, I think, 355 over pi r squared, so h is going to be 355 over pi times 3.837 squared. You end up with 7.675 centimeters. So the ideal soda can would have a radius of that and a height of that to enclose 355 milliliters, which is a centimeter cubed. What is super interesting is that what the soda cans that you pick up actually, is this the size of an actual soda can that you pick up? It's actually not. But if all things were equal and we did it with these constrictions, this is what it should be. But there are other factors in play. So